kind of topics would you like to revise?
Yeah, Deutsch-Jozsa and probably I'll find the slides.
Is it like before? Is it before this one or afterwards?
Let's start from Deutsch's office.
Okay. All right. Okay. Sure. Okay. So, anything in particular in Deutsch's algorithm, or should we just sort of go through it again, or what would you like?
Actually, I can't remember all the things. So
Okay.
actually
Okay. All right. So how about I just sort of quickly go through it again, and then you can stop me when things get confusing. So, yeah, Deutsch's algorithm is a quantum algorithm, and it's the first quantum algorithm that showed that there was a speed up. So that's why people are interested in this, even though it actually isn't really anything that solves any problem, but yeah. So it's a kind of an artificial problem, but it still shows a speed up. And so the problem goes like this. So it's a little bit abstract because, as I said, it's sort of a made-up problem. So let's consider all the binary functions with a binary input and a binary output. Okay? And with only 2 inputs or outputs, there's actually only 4 possible functions. And they're graphed here, right? So there's 2 flat, and then there's 2 that are sloped like this. And let's classify those 4 into 2 groups according to if they're constant like this, or if they're sloped, so basically the red or the blue ones. Again, it's sort of an arbitrary classification in a way, but again, it's for the purposes of showing that there's a quantum speed up. And basically the task is to figure out which, and so basically somebody then gives you one of these functions, which we are going to call the oracle, because it's like a black box, and then you can put a number in it, and then it'll tell you what the output is following one of these functions, right? But you don't know which one it is, so it could be any one of the 4. But the task is to figure out, okay, so is it in this blue group, the constant functions, or the balanced functions? That you want to kind of figure out which one it is, which group it's in. And the thing about this problem is that classically you need definitely 2 calls of the oracle in order to figure out which class it is, because the way that we've defined these 2 groups, constant means it's flat, but how do you work out if a function is flat other than at least you take 2 points and then figure out, oh, it's the same for each one, so it's flat, right? So you definitely need to know the output for two of these points, because otherwise you have no chance of figuring out which group it's in, right? So, you can, so it takes 2 calls of the oracle to figure out the answer to this task, right? This constant or balanced. And I mean, maybe you might, all this might sound a bit abstract, but the reason why we set up the problem like this is because, say, you're working out this function f on a computer, and we've just made it a black box, but suppose it's some complicated algorithm that you need to work out what the output is, right? So the number of calls of this black box is a kind of a good way to characterize how long your computer algorithm is going to take. Because suppose it takes 3 hours to get this output here, right? And then so if you know that each call is going to take 3 hours, then you've got to think carefully about how many times you're going to call the box, because 3 hours is quite a long time, right? So if you need to call it twice, then it's going to take 6 hours, and you don't want to wait so long. So you want to minimize the number of times you want to call this black box, or in actual computer language, maybe it's like a subroutine. Yeah. Okay. So basically, the idea of this whole algorithm is, and the kind of the trick that we're going to use in order to show that it's possible to calculate the output faster in a quantum computer, is that we're going to use this idea of the superposition, right? So because in quantum mechanics, you're allowed to put in a state like this, right? And because each one of those terms kind of proceeds in parallel, it only costs one call of this to figure out what the output is, because in a superposition, everything sort of happens in parallel. Only problem with what I drew here is that this is not really a unitary kind of process. So for example, if let's say I was looking at this function, the one that's flat, this one up here, fx equals 1. Okay, that basically means that the output is 1 each time. So basically that's 1, and so is that, right? And so this is a kind of a non-unitary process. It's a non-reversible process, and so it cannot really be done with according to our rules of quantum mechanics that we've learned. So it cannot be implemented with like a Schrödinger equation. So it's not reversible. So we must kind of tweak things a little bit. And so this is where this kind of setup comes in handy. And we started talking about this a little bit for Grover's algorithm. And so it's sort of useful there as well. Okay, so we have this particular construction. So instead of doing this on the previous page, which was not unitary, we can instead do something like this, where this is the input of the function that you're trying to evaluate, and here's the output. Okay, and instead of just making it f of x, which would just be, it depends upon the function, but if it was that constant function, then this would always end up being 1. Instead of that, what we can do is to do this addition modulo 2 on this particular input. And by doing this actually makes this whole circuit reversible. Okay, I don't know. Maybe we should do an example of this circuit. So maybe because this oracle thing could be the thing that is a little bit confusing. So we can just do a particular example. So for simplicity, let's choose that particular function that we're going to do the oracle for. Right? Okay. So this oracle circuit, so in this particular case, it's going to be y plus 1. And this modulo 2 addition, what that basically means this is actually actually same as the OR operation. Okay. So maybe I didn't really define this thing exactly, but basically this plus is the same as OR because, okay, so let me just draw the truth table for this one. So this is not even quantum, okay? So this is just I'm just defining what this operation means. It's a binary kind of operation, and it's defined like this. And it's actually the same rule as OR. Oh, sorry. I think, sorry, it's XOR. XOR is exclusive OR, yeah. Because OR is only true if, well, OR is true if one of these is true, right? But exclusive OR, so normal OR, this would be 1, but exclusive OR, this one actually is actually 0, because exclusive OR means sort of needs to be strictly OR. So if both are true, then that's not really OR. So when you say something like in English, if you say, okay, I'm going to go to the beach if it's sunny and it's on Tuesday, then you're certainly going to go to the beach if it's sunny. You're certainly going to go to the beach if it's Tuesday. Okay, what if it's Tuesday and it's sunny? What do you do then? Well, in normal kind of speak, probably you would also go to the beach, meaning it's true. But in exclusive OR, in that case, okay, no, you only go when one of those conditions is satisfied. Okay. So, so that's the truth table for this edition. But why do we use this? Well, basically because this is actually also the sort of the rule for binary addition, in a way. Well, the lowest digits of binary addition. So if I just did x plus y, and then if I'm working in base 2, then this is 0, this is 1, this is 1, and this is 1, 0, right? Binary. As in, that's 2. So this modulo 2 addition is basically like the lowest digit of this binary addition. This kind of thing is used in digital circuits a lot because you can create things like adders and things like that. So so basically this thing is basically addition modulo 2.
Does it have to be 2 or?
Yeah.
It might be modulo 3 or.
No, in this case, because we're generally using qubits, we're always going to use modulo 2. Modulo 2 is the sort of the natural thing to be using here because we're always sort of using qubits, and qubits are 2-level systems. It's also the natural kind of thing to use in classical computers because everything is digital, zeros and ones. That's also, basically modulo 2. So we generally use modulo 2. Okay, so so that's basically the meaning of that. Okay, so in terms of this circuit, so if we can draw the truth table. So these are the inputs here, and here are the outputs. So one of the outputs is just x. The other output is y plus, y modulo 2 addition of 1. So again, we've got the actually just the same. And y plus 1, what that means actually is that if we look at the table here, so if y is 1, then this x, so if y, okay, I'm trying to say, okay, it's confusing because we've got y plus 1, but if you add 1 to any, maybe we should be looking at this table. So that here's y, right, and then here's 1, okay, and then if you look in this, if you compare this column, which is the resultant of adding these two modulo 2, then you can see that this 0 becomes 1 and this 1 becomes 0. And so basically, y add 1 modulo 2 means actually just to flip y, because well, adding 1 in binary always just flips the digit, right? So basically here we just have to reverse what y is. Okay. So basically that's what this oracle here does, right? And later on well, next slide in fact, I showed that, I didn't really explain it, but there are separate circuits inside for each instance of these functions. So as I just sort of was describing here, for this particular function fx1, it's basically the output is just always the flipped version of y, right? So the y0 becomes 1, 1 becomes 0, and so that's why I drew this x gate here, because the x gate is the thing that flips it. Okay, so is that clear? So maybe one thing that I remember getting confused over this when I was studying this sort of as a student was that, okay, so we always talk about kind of like this, just the zeros and ones, but this is supposed to be like a quantum gate or something. So what about all the superpositions? You know, why are we only just talking about the 0 and 1 cases when actually this could be some quantum state? Right? So that's perfectly true, but actually if you know this, then you can always work out what the any quantum state is, because these are sort of, you can think of them as just special cases of the inputs, but most generally you might have an input state here that is like, call it A00, A01, A10, A11. Okay. And then let's say we put that state into this oracle, then basically what happens is have UF. What happens is that basically you just follow this rule that we've got drawn in this table for each of these terms. So the A00 term, the 00 becomes 01. Okay. 01 becomes 00. 10 becomes 11, and 11 becomes 10. So by just writing down what happens for these specific input states, we can actually work out what an arbitrary quantum state would be if it went into this oracle operation. Right. Well, I basically just explicitly demonstrated that it's reversible by just, okay, so if I just combine two of these gates together, then, okay, so one of these ones adds f of x to this output, right? Okay, and then now we're going to put that into another box like this. So it's going to be basically so here's our state x, y. Over here it's y plus f of x. And then we're going to put that into this oracle here again. And so this is going to be y f of x. So just to be sure, let's put brackets around that, okay? Because that's the that's the original value, which was used here. Here's the original value, and then basically what this oracle does is to add another f of x to it. Okay, so let's just work out with a truth table of so okay, let's work this thing out. So again, these are sort of the four cases that you can have. Whatever x is, depends on what x is, obviously, for f of x, but whatever it is, f of x is a binary function, and it can only be 0 or 1. Okay. So we're just looking at four cases of the f of x. Right? Okay, so we did here are modular addition rules. So basically it's this column is just a copy of that one. Right. Okay, and then now we're going to take this output and then we're going to add f of x into that, and we have to follow the modular addition rules here again. So 0 add 0 is 0. 1 add 1 according to this modular addition rule is actually 0. 0 plus 1 is 1. 1 plus 0 is 1. And you can see that this and this are the same. I did a little bit of shorthand. In fact, I just almost could guess it. But yeah, if you have two of the f of x's, then because so basically what I'm writing here is that so 2 times any binary number is actually always 0 modulo 2, because 2 times any number is an even number, and an even number in binary always has a 0 on as the last digit. So modulo 2, 2x is actually 0. So that's why 2 of f of x is equal to y plus 0, and then y plus 0 is always just y.
So 2 oracle actually did nothing. Like, if there are 3 oracles,
Sorry, 3 are? 3 what?
if there are 3 oracles.
Oracles, yes.
And then it actually equal to 1 oracle.
Yeah, yes, that's right. Yeah. So exactly, yes. So this I just basically kind of wrote down that the inverse of the oracle is the oracle itself. This is not always true, that the fact, usually the inverse of some unitary matrix, which is actually this is a unitary matrix, and basically any quantum gate is always a unitary matrix. Sorry, I meant to write the inverse of the unitary is actually conjugate transpose. It just so happens that for this matrix, any of these f's, conjugate transpose is equal to the u itself. So you don't have to even do the transpose, and you will get an inverse matrix. Just to sort of show you what kind of a matrix it would be. So when we're writing down the matrix form of this, what we want to do is we want to so UF in matrix form so I'm going to write down the 4 input states just to remind myself of what the basis is. Okay, so basically this table in matrix form would look like this. So that if you start with this state 0, 0, then the state becomes 0, 1. Okay, so we have to imagine we've got our vector here, and if the initial state is 1, 0, 0, 0, which is corresponding to that state, the output has to be 0, 1. So that basically means that we need this element to be 1 and all these other ones to be 0, so that when we multiply this matrix with the input state 0, 0, when we multiply with this matrix, the output of this one will be in this row. Likewise, we look at if the input is the 0, 1, that means it's 0, 1 means it's this one corresponding to this column. The output is 0, 0. So in that case, the matrix is this. If the input is this, and the output is that, so it's that. And the last one, 1, 0. Okay. So in matrix form, this oracle looks like this. And I was just saying that the inverse of this is the conjugate transpose, right? It's true for any unitary matrix. So, so we can write down the conjugate transpose of this. This is conjugate transpose, which we know also is the inverse of this matrix. Okay? And then, so I just have to transpose this, and then if there's any i's, I have to reverse the sign. That's basically what I need to do. So you can see that there's no i's, so I don't have to worry about the conjugate transpose. And then, so I just do the regular transpose, but actually this is symmetric, right? So it's the same. So it's just a special case. Some unitary matrices are their own inverse. This is just, it happens to be like that. In fact, I think if it's a matrix that doesn't have any i's in it, then I think it's probably always like that. So, yeah, I think that might be true.
Yeah. That if the matrix has an inverse, then the operation is reversible.
Yes, but unitary matrices, and we're always dealing with unitary matrices for quantum gates, are always reversible because they're always unitary. Unitary matrices always have an inverse like this. So for quantum gates, you never really have to worry that there is no inverse because by definition, they're unitary matrices. And
that's not your condition.
well, it's necessary in the sense that, you know, if we're going to write down a quantum gate, then presumably you are planning to implement it on a quantum computer, and if you write down a circuit with a gate that's not unitary, that basically means that it doesn't follow Schrodinger's equation, and if it doesn't follow Schrodinger's equation, it violates the laws of physics, and so the experimentalist will be angry at you because you are asking him to violate the laws of physics to do it, right? So it's basically impossibility. So in the sense that, you know, if you're writing a quantum circuit and you want it to be consistent with the laws of physics, it better be unitary. Okay. All right. So that's probably fine with that. And so we went through in a little bit of detail this particular choice of the oracle. But actually there's 3 others. And I don't know, maybe you want me to go through any of the other oracles? It's not, usually people don't even talk about this, by the way. What's actually inside the oracle. People just go, okay, there's a circuit that does it, blah, blah. I decided to include it to explicitly show you that, well, there is actual operation that you can do.
So the Y here is just another qubit, right?
Yes, Y is just another qubit, yes. So it's a 2 qubit gate, has 2.
So Y is now equal to Fx.
No, Y is not equal to Fx. Yeah, I see. Yeah, Y is just whatever you want to put in there. And the simplest choice, in a way, is to do it somewhere. Okay, well, I don't quite. The simplest choice, in a way, is just to set Y equals to the 0 state. And the reason why is then, if Y is 0, then the output of the oracle is always just X and then F of X. And so we sort of started this discussion basically because I was saying that it's not a reversible process. So I can't just have the X as the input of the oracle, because for some cases of the choice of this function, this is going to be a non-reversible process, right? But if I choose it like this, then it can be reversible, and so suddenly if I just set this to 0, then I just have X, and then 0 is the input, and then X, and then F of X is the output, and then that basically, you know, kind of implements my oracle. And over here I give basically an example of how you can also put in a superposition state. And so if you put like a Hadamard gate here, then the state at this point just after the Hadamard will be 0 plus 1. And then I've set this one to 0 because that's sort of the simplest case. And then basically on the output, what's going to happen is that I'm going to have this 0, F of 0, and 1, F of 1. So that's pretty much something like what I wanted to have in the first place. Originally I was thinking of something like this, where it's like F of 0 and F of 1, but Okay, that's not, doesn't quite work as a gate. So instead of that, I'm having this setup where we've got 2 qubits, and then we can have this superposition. Makes sense. We go through this circuit, or
So it was the Hadamard gate. I forgot.
yeah, Hadamard gate. Okay, so let's just go through that circuit. Here. And so we can work out what the action of this oracle does. So as with any quantum circuit, what you do is you just look at basically what the state is at various times. So right at the beginning, the input state is 0, 0. Okay. So at this point, the state, I'd write it like that. Over here, so the Hadamard gate produces the even superposition state. Which is, we've been calling the plus state. We introduced it a while ago in matrix form. This looks like this. So if you start in the state 0, what it does is to create this 0 plus 1 state. If you started in state 1, which is not the case, but just then you create the other superposition state with a minus sign in it. So, so at this point, the state, so on the first qubit, so we always have to establish some convention. So usually I just write the topmost qubit as the first one and the bottom one as the second one. So after the Hadamard gate is applied, the state is that. And, okay, so I'll write the tensor product symbol just to be clear. And because nothing's happened to the second qubit, so it's in 0. And in my usual notation, where I just kind of join together the qubits, so 0 tensor product 0 is the state 0, 0, and 1 tensor product 0 is the state 1, 0. So that's the state after the Hadamard gate. Okay, and then we follow the kind of the rules of the, well, the definitions of the oracle gate here. So, so basically, in general, another way to write down this oracle is if I've got x, y, applying this oracle gate, basically what it does is to produce y plus f of x. I've just sort of written down the same thing. As over here. So this is the first qubit, second qubit. That's the first qubit, which is there. The second qubit is y plus f of x. So that's the second qubit there. Okay. So
the second output should be plus 8 because it do not change.
sorry, the second.
The first qubit
Yes.
after the operation
Yes.
plus
Yeah.
and
Will be plus. Not exactly actually. So the way that this is, yeah, okay. So maybe I can see the confusion. So the way that this is defined is actually only in terms of this 0, 0 or 0, 1, 1, 0 states. So basically, I think, yeah, it's not quite correct to say that, okay, the first qubit is in this plus state, and because this thing does nothing to the first one, the first one will be still in a plus state. Actually, what you need to do is you need to look at each of these terms separately. So you need to say, okay, what is the rule for 0, 0? So we did this for this one. So we saw that 0, 0 became 0, 1. So if we were doing this particular oracle, so, well, we could do that. So let's take the particular case of fx equals 1. Yeah. So what we do here is we'd say, okay, 0, 0 becomes 0, 1. So the new state is 0, 1. 1, 0 is this one. 1, 0 becomes 1, 1. So for this particular example, the new state after the oracle would be equal to that. And sort of more generally, okay, so that was just for this example, but more generally, we basically follow this rule that I've written down at the top there. So for a state like 0, 0, so we can write down basically the cases explicitly. So y is 0 here, 0 plus f of x. And we know that 0 plus f of x is always just f of x. Right. 0, 1. And y is 1 here. So this is going to be, well, it's going to be the flipped version of f of x, which, how about we write sort of f of x bar, so not f of x. 1, and, sorry, I didn't quite do it right. So x is 0, so this is f of 0. Okay, so this is 0 plus f of 1, because x is 1. So this is 1 and f of 1. And the last one is 1, 1. basically this is the output for each individual case. And so, in this case, 0, 1, for the input of 0, 0, sorry, we need to look at this one. 0, 0, this becomes 0 and f of 0. And for here, for 1, 0, we need to look up this one. That is 1 and f of 1. Which is what I've got there. I mean, yeah, so maybe I went through that a little bit too fast the first time that we went through it, but basically it's sort of, you can kind of see it once you're used to it, of course, because if y is 0 here, then it's 0 plus f of x, and 0 plus f of x is always just f of x. So I can immediately know that if y is 0, then actually the output of this is always f of 0 or f of 1. So in other words, it's always f of x. Okay. All right. Then, yeah, so basically what I'm saying here is that, okay, so this looks nice, but, okay, so this is somewhat achieved, this would be like a first try at trying to make a quantum algorithm. This may well be what Deutsch did himself. Tried this and went, does this work? And if you think about it, it doesn't quite work, because you do this and you get that state, but then ultimately to get any information out, you need to actually measure something, right, in the quantum computer, because you can only get any information out of the quantum computer unless you do a measurement. So, if you just measured this qubit, these qubits, then essentially what would happen is that you get this term 50% of the time, and then you get this term 50% of the time. And then so you get the f of 0 half the time, just by looking at the second qubit. You get the f of 1 half the time. And remember, what we're trying to do is find f of 0, f of 1, right? But we wouldn't quite get both of those at the same time, because you need to run this, if you're lucky, twice. It's like sort of flipping a coin. You basically want one result, and then you want the other one. You want a heads and then a tails, right? So it's, it can happen either heads, tails, tails, heads, but then if you get 2 heads, then you have to flip the coin again, and actually you're doing even worse than the classical strategy. So actually kind of this doesn't work. It's only at best the same as the classical, because you'd have to run it twice at least, and maybe even worse, right? So this is actually a kind of a failed attempt, right? So that's why we look at this case, and this is where you need a little bit of inspiration, right? So it's like, okay, why would you think of putting the Hadamard on the second one? It kind of makes sense to put it on the first one, because then you get that superposition, and then you are evaluating 2 at once, right? It's sort of, that is the thing that you'd think would work, but actually that's not the one that works. In fact, the thing that helps you in the end is that you put the Hadamard on the second qubit, which is, sometimes you need this kind of mental trickery. So, so why does this work? Well, So basically, firstly, doing this part, 1 and then the Hadamard, I wrote this somewhere over here. So Hadamard on 1 actually makes this minus state. Okay. And then, how to explain it in a nice way. Yeah. Right. And basically what is happening here is that, so we prepare this minus state, right? And remember that this modulo 2 thing, yeah, this thing here, is basically like, yeah, so if it's a 1, if y is 1, it flips x, right? If y is 0, then it basically doesn't do anything. And so what happens here is that you prepare this thing with the minus superposition. And when you go through and you do the oracle, then because the oracle adds this f of x into the second qubit, it creates this state which is 0 f of x minus 1 plus f of x. And essentially what this does is it flips it. Yeah, if f of x is 1, then it flips both the 0 and 1. And if f of x is 0, then it doesn't do anything. Right? So it starts in 0 minus 1. If f of x is 0, then it doesn't do anything. If f of x is 1, it'll flip it. And because this is flipped, like it's 1 state minus 0 instead of 0 state minus 1. This one has an overall minus sign compared to what it was at the beginning. And so essentially what all this stuff does is that for the x's that f of x is 1, it puts a minus sign on it. So in a way the rule is, it's kind of, it's a long way to arrive at this point. But the rule is actually quite simple, which is that for the oracle with this particular input, basically the thing is that what u eventually does is to just put a minus sign on all the x's where f of x is 1. And this is actually true of Grover's algorithm too. So in Grover's algorithm, you have some, you can have all the different inputs, and then you apply the oracle, and then only on the terms where f of x is 1, it adds a minus sign. And basically that's the trick actually that makes this work and also Grover's algorithm work. Okay, so yeah, and then finally in Deutsch's algorithm, so you use sort of this construction where we have this particular input, and then you do the trick that you originally were trying to do, which was to make a superposition input of all the different states. And then when you do that, what basically happens is that if you had this input state that was 0 plus 1, then the output will be either 0 plus 1 or 0 minus 1, depending upon which of the 4 functions you have. And you can see that the output is exactly, has a relative minus sign if it's balanced, and it has a relative plus sign if it's constant. And that's exactly kind of matching up with what we had as our task. I mean, in fact, probably what Deutsch did, which I don't know, but is that he noticed this fact, engineered the problem so that it would solve it, and then go, hey, look, this solves that problem, right? so sometimes you have to be very creative in what you do, but actually, because this exact same construction of this, putting the minus sign on the second bit, because that was used in Grover's algorithm, and Grover's algorithm is an actually useful kind of quantum algorithm with maybe a huge number of applications. So even though this was sort of a made-up example, eventually it became super useful elsewhere. So yeah, you can do so eventually it's all useful. Yeah, and so finally, basically, all you have to do is do a measurement in order to distinguish between the plus state and the minus state. And that you can just do by this combination of Hadamard and this measurement. So you can think of this Hadamard as, if you apply Hadamard on this 0 plus 1, then if you do Hadamard on the plus, so that is 2, 1, 1. That's the Hadamard gate, and then the plus state is 1, 1. So if you just do this matrix multiplication, then you'll find it's 2 and 0, so it's 1, 0. So plus turns into 0. So Hadamard is another example of a unitary that is its own inverse. Right? So you apply Hadamard twice. So you apply Hadamard on 0, it becomes plus, and then you apply Hadamard again on plus, then it becomes 0. So it's its own inverse, and you can write it as H squared is identity matrix. H of minus becomes 1. And so what we've got here is that we've got the output of the oracle, and it is applying this Hadamard here, turns it into this 0 state, and so we can figure out if it's constant or balanced just by looking at the readout here and noticing whether it's 0 or 1. Oh, and the great thing about this is that we did this all by only calling the oracle once. So the oracle, so this is like a factor of 2 speed up compared to the classical case. Classical case, you have to call the oracle twice to figure out what the whether it's constant or balanced. In this case, you can do it just with 1 call. And for Deutsch-Jozsa algorithm, which is some kind of generalization, we're not going to go into it, but this is some, basically souped up version of Deutsch's algorithm, and in this case, the speed up is actually 2 to the power of n, where m is the number of qubits in this bigger oracle. So this is, I think this was one of the first examples that showed like a huge speed up over classical computers. All right. Any other topics to revise? We could do more revision if you like. Next lecture too.
We can do tomorrow lecture.
Ah.
It still has something about grammar algorithm.
Hmm.
And
So you had something in Grove's algorithm we started talking about last time? Or? Yeah, okay. Okay. Okay, so Grove's algorithm. So basically it's a database search type algorithm. And as I was saying, this is actually much more practical in a way than Deutsch's algorithm. And the idea is to find an element in an unsorted database. So this database here is sorted in alphabetical order, but unsorted in any of the other entries like license numbers, addresses, cities. So the idea is to find one of these entries, and classically, really the only way to do this is to go through one by one. So because there's just no organization to the database, basically no strategy that you can really follow. So the time that it would take, and if you call the kind of the unit time to look at the database, if you say that that's 1 unit of time, then it would take basically n units of that time to find it, because it could be at the beginning, at the end, or anywhere. Right. So again, we encounter this oracle, and in Deutsch's algorithm, we were using this function. We were actually looking at all possible functions, right? So we had a binary input and a binary output. In this case, actually, we have a binary output still, but now an input which is more than binary, right? Like it's bigger than, it's got n elements as its input. This x variable goes from 1 to n, I think, is the notation that we'll be using. Maybe not on this slide, but later. So we want to find, and then this function is defined such that f of x is 1 if it's the solution, that's the thing that we're looking for, and if it's 0 otherwise. So, and generally, this function kind of looks like a sort of a spike. So if you were to plot this, function, it would, you can imagine it to be mostly 0 everywhere, and then there's a couple of spikes somewhere, and those are the things that you're looking for. And again, we can think of this f as being some kind of black box where we don't really know the inner workings. Well, actually, we could know the inner workings, but even if you knew it, it's actually still hard to find what the output. Sorry, it's hard to find the input such that the output is 1. Basically, it's hard to invert this function and that's actually quite a natural or a common type of thing that can happen because some types of operations are hard to kind of invert. Example was factoring numbers. Factoring numbers is kind of generally hard, but multiplying numbers is easy. Okay, and so we encounter this quantum oracle again, and because, again, the same reasons as Deutsch's algorithm, we need basically some kind of circuit that is invertible and still kind of encodes this function f, which contains all the information about this search problem. Right? So again, we basically use exactly the same construction. So the only difference is that our input x is not just one qubit or one, it's a whole range of qubits because this x is now a binary variable that goes between 0 and n minus 1. So little n is 3, so if I've got 3 qubits, then this goes from 0 to 7. 8 elements in total. And the other one is exactly the same as what we had before, because the output of the function is still binary. So 0, it's 1 if it's the answer that we're looking for, 0 otherwise. So the output is still binary. So this bottom one is just 1 qubit. And again, we do the same thing where we're doing this modulo 2 addition. So it's exactly the same as Deutsch's thing. And we're going to use, again, the same trick that Deutsch used, where instead of having a 0 as the input, which might be the natural thing that you might think of doing, we actually always set this bottom input qubit to this minus state. And that's the trick that makes this oracle behave in such a way such that if you have x as your input, then basically it will produce a minus sign on all the x's where f of x is 1, right? So minus 1 to the power of 0 is plus 1, minus 1 to the power of 1 is minus 1. So this one will be a minus sign only if f of x is 1. So, assuming we just set this bottom thing to minus, the minus state, actually we can kind of forget about this bottom qubit because nothing ever really happens to it, and it was sort of only there because, we wanted to use this Deutsch trick, right? But if we just set that to minus, then we can actually just about forget about it. I mean, okay, maybe you need it in the physical implementation if you wanted to do it exactly like this, but for our purposes, it doesn't really do anything for the rest of the algorithm, so we can just kind of forget about it. So essentially what this oracle does is just to, in the end, it's a bit of a long story with Deutsches and all that, but in the end all it does is just to put a minus sign on the x's where f of x is a solution. So henceforth we can just sort of say that this is what the oracle does. I think that's as far as we got. Yes, that was as far as we got. Any other questions? No? Okay, well, maybe we'll leave it there. So you guys are both presenting next week, right?